Hello and welcome to our video covering topics in section 4.3 of your textbook. In this video, we'll be discussing the matrix representation of a linear transformation between abstract vector spaces, as well as something called the change of basis matrix. Let's jump right on in. First, let us recall a simpler time, say 2 weeks ago. In this simpler time, we thought of x as a vector in Rn, so x is just some list of numbers, and a transformation of x into another list of numbers we would represent as multiplication by some matrix A. And we weren't worried about anything like coordinates or anything like that. It was just, we've got a list of numbers, take it to another list of numbers. That's multiplication by a matrix. Then geometric considerations about, well, really, matrix multiplication, these linear transformations are actually somehow geometrically changing a vector space Rn. And that made us think, well, maybe there are different coordinate systems that would be better for describing a linear transformation. And so then we started to worry about, well, okay, what if we had some new basis v1 to vn of Rn, and now we write our vector in the coordinates of this new basis, and we write the transform vector in the coordinates of new basis. And now we have to wonder, how do we get B? Or if we have B, how do we get A? So yeah, how would we find B in this situation? And what we realized is that, well, okay, we can actually translate back and forth between a vector in what we now think of as the standard basis and a vector written in the new basis with this matrix S, where S is actually just, well, the columns of S are the vectors of the new basis. And so it turns out, okay, you just multiply this coordinate vector by S and you get your original vector you get the vector in standard coordinates. And then we kind of have this diagram showing us what's going on. We can go from x in coordinates and back into standard. Same with the transformed vector in the coordinates. We can transform that back into standard coordinates. And we realize that, oh, well, if we want to get this matrix B, one thing to do is first do S inverse, then do A, then wait. First do S, then do A, then do S inverse, right? S, then A, then S inverse. And that will be some matrix that we get at the end of that, and that matrix is going to do the same thing as B. And so B is that matrix. We also have another way of finding B. So another option we could have done is sort of brute forcing it, where we just construct B column by column. Where we say, all right, well, B is, you get it by taking your first basis vector, transforming it, and then writing that transformed vector in terms of the column, in terms of that new basis. And same for each basis vector, transform it, and then write it in the coordinates of the new basis. And that's another way to construct that same matrix B. So, okay, where are we now? Well, now, instead of being in Rn, where we've just got a list of numbers, we're in some abstract vector space, possibly a function space. And so we've got some abstract vector and some linear transformation on that abstract vector space that takes us to, let's go back a second, that takes us, to some transformed vector. And so we've got this abstract linear transformation T. And we've seen, because of a correspondence between finite dimensional vector spaces and Rn, that we can pick a basis and think of that abstract vector as, we can pick a basis, we can write it in the coordinates of that basis, and then have the coordinate vector. Similarly, with a transformed vector, we can write that in the coordinates of the new basis, and then we have a coordinate vector. And now the question is, well, how do we get from this coordinate vector of our abstract vector to the coordinate vector of the transformed vector? So how do we find this matrix? Like this T, this is an abstract linear transformation, but B is a matrix. How do we find that matrix? Well, we draw another diagram and we say, all right, well, we know how to get from a vector to its coordinate. It's just from the coordinate vector, we do this coordinate transformation that we saw in the last video. And so in some sense, as transformations go, B is the same as first doing the inverse coordinate transformation, then T, then the coordinate transformation again. But that's not exactly a formula for calculating B like it was before, because before we just had matrix, 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 multiply 3 matrices together, you get a matrix. But here, this is like abstract linear transformation, abstract linear transformation, abstract linear transformation, which gets you from here to there. So they get you, they start and end at the same place. But how does that get you B? I think really what we've got to do is we've got to kind of brute force it. So if we want to find this matrix B that takes a vector in its coordinates to the transformed vector and its coordinates relative to the basis, well, okay, if you've got this basis F1 to Fn, then B, you construct it column by column. You take the transformed F1, write it in the coordinates B. And so on and so forth. Take the transformed Fn, write it in the coordinates. I guess I shouldn't be calling this B. Let's call this pretentious B. So in coordinates pretentious B. So that is how we get our matrix B. Now let's see these ideas in action. So example 2 in your book is, all right, let's use theorem 4.3.2, what we just saw, to find the matrix B of a linear transformation f from that takes a function f, takes its first derivative, adds it to its second derivative. And let's consider this only on the space P2 to P2, so the space of polynomials of degree less than or equal to 2. And let's do this with respect to the standard basis for P2, which is the function vectors 1, x, and x squared. That's our basis. So, okay, if we're building this column by column, what we want to do is we want to take this first basis function, transform it, and then write the transform in the coordinates of this basis. Similarly with x, now we'll want to take its transform and then write it in the coordinates of this basis, and then same for x squared. So let's do it. Let's transform 1. So transform of 1 takes 1 prime plus 1 double prime. Both of those are 0. And so what is 0 in this basis? Well, it's 0 times 1 plus 0 times x plus 0 times x squared. So the coordinate vector is going to be 0, 0, 0. All right, let's look at what happens to basis vector x. X prime is 1, x double prime is 0. So we get the transformed vector tx is 1. And what is that in terms of our basis? Well, it's 1 times our first basis vector plus 0 times our second plus 0 times our third. And let's do it now with x squared. Okay, first derivative of x squared is 2x. Second derivative of x squared is 2. And so what is this in terms of our basis vectors? Well, this is 2 times the first basis vector plus 2 times the second basis vector plus 0 times the third. So there we go. Putting it all together, our matrix B is going to be equal to this matrix. And let's stop for a second and think about how kind of cool that is. That we just had an abstract function space, took an abstract linear transformation like differentiation, and said, okay, take a function, add its first derivative to its second derivative. And that amounts to, in linear algebra land, multiplying by this exceedingly simple matrix. That is pretty sweet. Okay. Now, onto the topic of change of basis matrix. I mean, there are other examples in your book, and I encourage you to read them. I demand, actually, that you read them. But okay, change of basis. So if pretentious U and pretentious B are two bases of a linear space V, then what is the relationship between the coordinate vectors, f written in the coordinates of pretentious U and f written in the coordinates of pretentious B, for some element? So, okay. Let's look at another diagram. This is just really to map out what is happening. So we start with some abstract vector f and some abstract linear space V. And we say, okay, well, we have two sets of coordinates. And if we want to write our abstract vector f in pretentious U coordinates, well, we've got the coordinate transform with respect to pretentious U that'll take us there. But if we have another basis, pretentious B, okay, well, we could do the coordinate transform to take us to the coordinates in pretentious B. And then the question is, what's the relationship between these two coordinate vectors? What is this S? This S is going to be a matrix because this is a list of numbers and this is a list of numbers. They're both coordinates. How do we find S that gets us between the two? So, okay, from like a diagram perspective, going from F in pretentious B to F in pretentious U coordinates is just, well, okay, you can do S times that vector, or you can go back, do L sub pretentious B inverse, and then do the coordinate transformation with respect to pretentious U. And that these are going to be the same given kind of how we've set things up. So S here is going to be called the change of basis matrix. And given how we drew the arrow, it's going to be the change of basis matrix from B, pretentious B to pretentious U. I mean, is it worth it for me to continue, say, pretentious before both of these? I mean, from a time efficiency perspective, certainly not. Even from a gag perspective, it's going to get old, but I'm going to continue to do it because I can. Anyway, and this is sometimes denoted S from pretentious B to pretentious U. Okay. Okay, here's our pretentious B basis. We've got basis vectors B1 to Bn. Then finding the matrix that goes from these coordinates to these. To get that, the claim is, all right, well, first, what happens when you first do the inverse coordinate transform with respect to pretentious B? Well, you just get your original basis vector back, but kind of a coordinateless basis vector. And then you do the pretentious U transformation of that. And so that's what this is doing. This is saying, all right, whatever your first basis vector was, sure, you could like write it in the pretentious B coordinates. Undoing that takes you back to B. And then doing the coordinate transform with respect to pretentious U gives you this. And that's going to do the same as just having done S itself on that vector. And so you do this for all the basis vectors, and there you go. You've created your change of basis matrix. So this is how you create, kind of by brute force, column by column, you create a matrix that goes from a vector written in one set of coordinates to the same vector written in a different set of coordinates. So let's see these ideas in action. Okay, example 5 from your book. Let V be the subspace of C infinity. This is a set of infinitely differentiable functions. And let V be the subspace spanned by the functions e to the x and e to the minus x. With bases, so now we're going to have two different bases of this subspace. One is kind of the natural one given how we've described it. It's going to have basis vectors e to the x and e to the minus x. The other basis is going to have basis vectors e to the x plus minus e to the x, and then e to the x minus e to the minus x. Unless you think this is just like a completely arbitrary second set of basis vectors, like just notice this is essentially hyperbolic cosine, and this is essentially hyperbolic sine. And so these are actually like natural functions in and of themselves, and they end up spanning the same space. So, okay, you have kind of two natural options for this two-dimensional vector space. Let's find the change of basis matrix that takes us from the constant multiples of hyperbolic cosine and sine to e to the x and e to the minus x. So, okay, let's do this. Recall, this is how it's defined. And so what is going to be our B1 here? Well, we're starting at this pretentious B basis. So our B1 is going to be e to the x plus e to the minus x. And then we only have two basis vectors, so our B2 is going to be e to the x minus e to the minus x. So we're going to write something like that. And now we have to determine what are these functions in the coordinates of pretentious u. Well, e to the x plus e to the minus x is just 1 times the first basis vector plus 1 times the second basis vector. So we're going to write it like that. Too easy. All right, let's look at the second one. Again, not too hard to see. All right, it's going to be just 1 times the first basis vector plus minus 1 times the second basis vector. And so the coordinates for this vector in the u coordinates is going to be 1, negative 1. And so our change of basis matrix from pretentious B to pretentious U is going to be 1, 1, 1, negative 1. That's not so bad. And I think in terms of problems you'll see in this class, these calculations like converting from one basis to another won't be so bad. In general, though, that can be hard. It can be pretty non-trivial, especially if you have like infinite dimensional function spaces and you want to write something in terms of polynomials and then convert it into, say, sines and cosines. Like, yeah, it might not be totally obvious how to do it, and you might need some theory. But I guess it's just not acknowledging like going back and forth between these two matrices is not always going to be just like, oh, there it is. Unless you're, in first semester linear algebra class, then it might be that easy. Okay, let's end on one final note. So let's now consider a linear transformation from some abstract vector space to itself, where this abstract vector space is finite dimensional. And now let's have two different bases of this space. We'll let A and B be the coordinate matrices. I don't want to say this. Well, okay. A is the pretentious U matrix, and B is the pretentious B matrix of this transformation, respectively. And then now the question is, what's the relationship between the matrices A and B? And then also the change of basis matrix. Like, how are these all related? Okay, so we're going to draw another diagram, just keeping track of everything that's going on. So first, we've got a linear transformation from some vector space to itself. If we have some function in the vector space, it gets transformed by this abstract linear transformation T. And then, okay, if we wrote this function in coordinates pretentious U, in its transformation in coordinates pretentious U, then going back and forth between these honest-to-goodness vectors in Rn, that is done by multiplication by the matrix A. Similarly, okay, if we have coordinates pretentious B, then this transformation is represented by multiplication by the matrix B. So, okay, how are all of these things related? Well, okay, we know how to get from this abstract vector F to its coordinates. We just write F in terms of its basis, and we take the coordinates in terms of that basis, make it a vector. This is the coordinate transformation. So to get from here to here, we do the coordinate transformation, similarly from here to here. And then the same exact idea going on with relationship to pretentious B coordinates. You have your vector, your coordinate transformation takes it to its coordinate vector for both the function and its transform. And then, as we just saw, we have a matrix that can go back and forth between a vector written in one basis and that same vector written in another basis. And that matrix is the matrix S. And so, keeping track of our information in this way, now we can see a relationship between the transformation, or between, the multiplication by matrix A and multiplication by matrix B. And it's very similar to something we've seen before. No pun intended with the use of similar. I just made that up. Okay, so what are we saying? We're saying, all right, let's suppose we start with F written in pretentious B coordinates. Then to find B in terms of A and S, well, first we do S, then A, then S inverse. So this is saying that to get B, you first do S, then A, then S inverse. Similar, if you want to do A, or you want to find A, you do S inverse B S. So S inverse B S. And then, whoa, that was a little premature. B and then S is the same as doing S inverse then A, or let's see, S then A is the same as doing B then S. That's what this is saying here. S then A is the same as doing B then S. Okay, and that will do it for today. See you in the next video.